Awesome, everybody. I hope that was a nice little review of Newton's first law and Newton's second law, and an introduction to Newton's third law about action and reaction. Every motion has an action and a reaction, which is why your bicycle actually works to move forward. We're going to spend all day talking about that action-reaction cycle, so don't worry if you don't quite understand it yet. That's so okay. This is what we're here for the next hour and a half together. All right, so we're going to go over and look at that, use the link to see the page where we read about Newton's third law, and then you're going to come back to me again, and I'm going to talk a little bit about what we just read. So students who are live in the classroom next to me, we're going to look at that link together. Everyone else, you're going to pause this video and look at the link and then come back to this video. Today, there's a lot of pausing and moving backwards and forwards. Sorry about that. I hope you don't mind. Okay, so live students, everyone, I'm going to walk you over and share my screen with you. Then the rest of you need to pause the video. And live students, you're going to come back and look. Okay, I hope that was clear. That felt a little unclear. But let's start with the first step, sharing the video. So this is probably what you're seeing now. You want to move over to Google Classroom, and here we're all going to read this. If you're sitting in the next room, we're going to look at it together. If you are not, you want to pause this video for just a moment so you can have a chance to read it. And then you're going to answer this question. Today, there are no Google worksheets for you to work on, but there are questions after most of the videos. All right, so you're going to just click that, and it will give you a chance to have some space to write your answer. But don't do that until after you've read Newton's third law of motion. All right, we're going to pause this recording, and live students, we're going to go over there together. Here we go. Okay. All right, everybody, you just saw an explanation, sorry about that, of Newton's third law of motion. In words, it's actually the very simplest, right? For every action, there's an equal but opposite reaction. Now, the words equal and opposite are actually really important in that. It's not just for every action there's a reaction, but that reaction is always equal and opposite. That means forces always come in pairs. Every time one thing exerts a force in one direction, there is an equal and opposite reaction in the other direction. Now tomorrow, this is going to get even more important because tomorrow we're going to take all three of Newton's laws and apply them to the universe as we know it. We're going to talk together about why the Earth orbits around the sun and why the moon orbits around the Earth. And that equal but opposite reaction is going to be even more fundamentally important for life as we know it on this planet. Today, I just need you to remember action, equal and opposite reaction. And I drew a little picture to make it a little clearer. So here we have my incredibly artistic drawing, sarcasm, of a rocket. Here we see the fire from the boosters in the rocket push down, right? It's the action. The fire pushes down upon the Earth, and the equal but opposite reaction is the Earth pushing back on the rocket ship itself and the rocket ship flying into space. We have an action and an equal but opposite reaction. Now, if this wasn't the way our Earth worked, if this wasn't just true, none of the sports games that you enjoy, whatever they might be, would be possible. If I didn't, when I had a basketball in my hand, if I didn't dribble down and it bounced back up, basketball would not be possible. If in football, if one person wasn't able to tackle another, right, what would be the game? If in tennis, you couldn't pull back, hit a ball, and have it actually go somewhere, which is part of the action and reaction cycle, there would be no tennis. And we could go on and on. Sports are not possible without the reaction, action-reaction cycle. These things really matter in our everyday world. And we're going to keep looking at them together. We're going to start by another little video. And this video I think is going to be really helpful for you because it shows the action-reaction cycle in space. Now, space is special because why? There is no gravity, or there's much less gravity depending on where we are in space. This video happens on the International Space Station. And on the International Space Station, the astronauts are basically floating around. Gravity isn't acting upon them. So we're going to see one astronaut as he exerts a force, in this case, pushing various things of various mass. And we're going to see the reaction they have upon him. Because this equal but opposite reaction, the force is always the same. The action and reaction force is always equal. But the thing with the lesser mass is the one that moves. Let me say that one more time. The force that the thrusters apply upon the Earth and the Earth applies upon the rocket are always equal. But because the rocket ship is much smaller, has a much smaller mass than the mass of the entire planet, the Earth doesn't move when that rocket ship takes off. The rocket ship does, right? So I could have drawn here, I don't remember where I put my blue pen, but I could have drawn here some of the globe. It won't move. However, the rocket ship will. You can see this or practice this wherever you are right now if you get up from your chair and you try to jump. So here I am. You can't see my feet, but my feet are firmly planted on the ground. Now, in order to jump, I'm going to have to push up off of the ground. So I'm going to exert an effort down into the ground and push up off the ground. Now, I promise, with my mass, this room and the floor below it will not shake. My jumping does not shake the Earth. However, the Earth, because it's so much bigger than I am, exerts a force upon me that allows me to move up. Here we go. And there we are. Try this at home yourselves. All right, so now we're going to go back to our astronaut video. It's called the STEM mechanics video. I'm going to screen share with you and show you exactly where it is. And we're going to watch how this works in space. So I'm sharing my screen. Here we are back to Google Classroom. Right underneath what you've just done. And I hope, see, I just refreshed my Google Classroom. Give me 1 second. There we go. I can see that 3 of you so far have answered that question. Well done, you 3. Here we go again. Here's the STEM demonstrations, is what's called, of Newton's third law in space. After you watch the video, you've got another question to answer. So once again, you're going to push on this, watch the video, and then push on this, and you'll have a space where you can answer this question. Question's not going to make a ton of sense until you watch the video, but I will read you the question now just so that you have it in your head. We're going to see an astronaut named Mark and another astronaut named Joe. So the question says, now imagine that NASA astronaut Mark could have an elephant up there in the space station with him. Would be a little tough, wouldn't it? If Mark tried to push the elephant the same way he pushed Joe, what do you think would happen? Hint, think about what has more mass, the elephant or Mark. Based on who has more mass, who would be most likely to move the most? That question's going to make a lot of sense once you watch this video. So we're going to stop this recording of me. You're going to watch this video and come back to the next recording. Here we go, everybody.